In a moment, I'm going to have you folks work this problem out on your own. I just want to point out something very, very important, and that's this. The natural log of x, quantity to the x, is not the same as the natural log of x to the x. This is the natural log of a power. What I'm plugging into the natural log function is itself a power. This is a power of the natural log of x. The power rule for logs applies to this thing. If the argument of log, if the thing I'm plugging into log is a power, I can bring that power down and make it an exponent. So this one here is x times the natural log of x. This is not x times the natural log of x. This is a power of the natural log of x. And in general, if I had a to the x and I tried to say that's x times a, you'd say, no, it's not. We don't have a rule like that. That's what I'd be doing here. Okay. I can only apply the power rule if the argument of log, the input to log, is itself an exponential expression, which this is not. Okay. So I'm going to have you pause the video and try to work this out using logarithmic differentiation. Okay, so the first thing I want to do is just write this as an equation. Y equals the natural log of x to the x. If I wanted to keep it as f of x, I certainly could. I'm just used to, when I use implicit differentiation, calling my function y. But it's just a question of notation. If I wanted to keep it as f of x and then take the natural log of f of x, that would be totally fine. Okay, the reason I need an equation is because I'm going to do the same thing to both sides. I'm going to plug into the natural log. This log isn't helping me because the argument of this log is just x. So I don't have any rule that allows me to simplify a power of a log. So I'm going to say the natural log of y, and I can do that because I know that y is positive, because I have this definition that the domain of this function is everything that makes the base positive. All right, so this is going to become the natural log of the natural log of x to the x. Now I have a power in the argument of that natural log. So I can use the power rule of logs and bring that x down in front. So we have the natural log of y is equal to x times the natural log of the natural log of x. This is a product of two factors. X is the first factor. The second factor is this composition. This is plugging the natural log into the natural log function. That is not multiplication, that's composition. Okay, so we take the derivative of both sides. The derivative of the natural log of y is equal to the derivative of x times the natural log of the natural log of x. On the left side, we get 1 over y prime. On the right side, we use product rule. So we get the derivative of x times the natural log of the natural log of x, plus x times the derivative of the natural log of the natural log of x. 1 over y prime equals, derivative of x is just 1, so we're left with the natural log of the natural log of x, plus x, and this is a function composition. So the derivative of the natural log function is the reciprocal function. So I'm going to take the reciprocal of the natural log of x. And then I'm going to multiply that by the derivative of the inside part, which is the natural log of x. So we have 1 over y prime equals the natural log of the natural log of x, plus x times 1 over the natural log of x, and then the derivative of the natural log of x is just the reciprocal of x. And I can go ahead and cancel those x's, because since x is plugged into the natural log, I still have the information here that x isn't allowed to be 0. So 1 over y prime is the natural log of the natural log of x plus 1 over the natural log of x. And then y prime is going to equal y times this quantity, the natural log of the natural log of x plus the reciprocal of the natural log of x. And since I have an explicit formula for y, I want to replace it with that formula. So y was the natural log of x to the x. That gets multiplied by the natural log of the natural log of x plus the reciprocal of the natural log of x. So there's my final answer for the derivative of this function.